virus detection purpose. So the motivation behind this developing this platform technology for sensing is mainly we want to have a versatile platform for making a level-chip sensing devices, so they can be used in all sorts of point of care or healthcare related applications. So as you can see from my title, that the approach that we're taking is a optofluidic methods. So just very quickly looking at what is optofluidics, basically combine optics and microfluidics. So using we study the light matter interactions, and then we combine with the control and manipulation of a small volume of liquid, and we combine all this together to use for biosensing. Because of the light and matter interactions, can be performed without any labeling of your analytes, and also you can easily incorporate it into small devices. That's why we think it's a very attractive feature to have in our level chip devices development. They are like many optical methods we can use to combine with microfluidics for sensing. So what we've been looking or focusing on is optical methods for whispering variable microsphere lenses. The name is long, but the principle is quite simple, because if you're familiar with surface plasmon resonance, it's quite similar with this based on some total internal reflections happens on the interfaces. But the objects we're looking at is microspheres. So basically, you can see from the surface plasma resonance on the flat surface, we have total internal reflection. In this case, the total internal reflection happens on the curved surface, basically on the interfaces between the microspheres and the surrounding environment. When you have the light shines on, usually it's a laser shines on the spheres, we generate this total internal reflection. And then we will do quite sensitive object signals. There are basically two modes of whispering variable generated from those spheres. One is passive mode, like looking for through a passive medium. Basically, you have a laser couples into your spheres, and you start this total internal reflection process. Another one is you doped your microsphere with a GaN media. Usually, it's a fluorescent dye. You just normally like general illumination process shine a line to excite your fluorophore, or the dye inside your sphere will emit light when you start with total internal reflection generating whispering variable. Because the light interact a lot with the on the interfaces with the surrounding environment. You can imagine it's very sensitive to whatever changes on the surfaces of your microsphere. So as shown in this, on the right hand side figure, if you have a protein that binds to the surface, they usually will change the resonance frequency. And then by looking at this shift of the frequencies or the wavelength, we can relate it to how much changes is happening on the surface of the microsphere. So this is how this sensor basically works. So when we want to combine these two microfluidic platforms, eventually relate devices, we can see that some papers that showing there's some work working on these areas already, but you can see most of them are using a pump to drive liquids through the microfluidic devices, or even some of them will have the detection unit, as shown in the right hand figure, outside the chip. So that's not really sort of like on the chip we want to do. So our lab has developed sort of a pump-free microfluidics to combine with optical methods for some sensing devices. There are also been a lot of research that people want to get rid of the pump, get rid of the excess accessories to operate or manipulate the fluid. Like they usually call that passive microfluidic platforms. They're based on capillary force, gravity, osmotic pressure, etc. But what our group has come up with is evaporation-driven microfluidics. Basically, it mimics the transpiration systems of plants. So we well know that if you have trees, the leaves evaporate water, that will generate the force to absorb the water actually from the ground via the roots. So a bit more detail on what these pump-free microfluidic platforms we developed looks like. It basically is a micropillar array made of quartz. We make these devices based on the standard lithography plus reactive dry etching process. So these micropillars, they are 10 to 30 micron size, and the height can be 20 to 50 microns. And what we want the microfluidic dimensions to be. And then the whole chip's dimension is millimeter by 10 millimeters. And because it's made of quartz, it's hydrophilic. So when we add some liquids into sample loading zones, as you see from the left side video, the capillary making can be observed. So you form a very nice equilibrium on your micropillar array. And then because this is an open system, so we don't have a thing. This is not a closed like a normal microfluidic channels. It's open, so the liquid will start evaporating when you have this liquid film formed between these pillars. Then when we add a second liquid on the sample loading zone again, the evaporation of the first liquid will drive the second liquid feeding to the pillar array. So as long as we always have the sample loading zone of second liquid, this evaporation value flow will be continuously going on and on. You can see from the right hand side the view there. So the purpose is to combine this pump-free microfluidic platform based on micropillar array together with the respiratory microsphere that I was talking about to do some same thing. So the model analyze shows here is a virus. Basically the influenza virus. You know that it's important to get these viruses without going to the lab because we are this complex process. So the idea is we put these microspheres in between those micropillars. So we made the size of this we made a gap between the pillars to get the size of the microsphere. So the microsphere is trapped there. It will not move this position there. So when we start loading samples that contain viruses, the evaporation will drive this sample that contains viruses, so it charges microspheres. And these microspheres we can modify them with antibodies, so antibody will capture those viruses. And then in these microspheres, when these viruses that bind to these microspheres, we change the respiratory mode, so we can detect these viruses through optical shift that we observe from the spectrum. So for biosensing, as I mentioned, we need to have antibody coated spheres. So this is basically what we use to coat influenza A antibody on these surfaces. I also want to point out that the microsphere is so typically the fluorescent dye, as I mentioned previously, and actually using the active media inside this whispering microsphere resonators. So when we shine laser light onto this microsphere, the fluorescent dye will emit lights then generate the process. So once we have this antibody coated microspheres, we basically put it onto the micropillar array. If you can clearly see to the right hand side as the image those spheres that we normally check between pillars, so we will not move its position during our measurements. So how these optofluidic sensors works? So we have seen the video, but this is one of the steps that operation of these sensing platforms. So we will have this microsphere check between pillars. Then we have virus containing samples put into the sample loading zone. Once the evaporation happens, you can see the virus containing samples will flow more to the inner array, and the virus is flowing out of the microsphere and be trapped. And then we use a laser light to shine some of the microspheres to monitor how the spectral chips look like. So when we plot the spectrums over different times of measurement, so basically we're continually supplying these. Okay, we're continually supplying this virus sample into the system. We measure like up to 24 minutes consistently rescue the virus by using micro. And we also perform a controlled experiment with the virus, which is not specifically bind to the antibody that we're using. You can see the red dot, it doesn't really shift much. And then we also do another thing is we cover the array with a cover slip that will stop evaporation repeatedly. So we basically restore flow there. So we're not flowing, and we don't really observe any shifts in 30 minutes. So it's really showing the evaporation flowing plays a very important role in our system here. So quickly summary, I've shown this detection of influenza A viruses to show how important it is evaporation flowing flow that can help us detecting different analytes. So finally, thanks to the funding and the pressure